Hello children, today we are going to discuss remaining sums of exercise 1.2. Before going to that, we have to know what is fundamental theorem of arithmetic. What is fundamental theorem of arithmetic? Every composite number can be expressed as product of primes in which the prime factorization is unique apart from the order in which they occur. What is the meaning of this? For example, if you want to do prime factorization of 54. So how can we write 54? How you will do? We will do in this way. First we will take 2, 27. In 3 table 9 times. 3 table 3 times. 3 table 1 time. You may write like this. 3 table 18 times. 2 table 9 times. 3 table 3 times. 3 table 1 time. So 54 can be written as product of primes. Product of primes in which the prime factorization is unique. What is the meaning of unique? Same. 2 how many times occurs? 1 time. 3 3 times. Same prime factors are there. Here also 2 1 time, 3 3 times. So prime factorization is unique apart from the order in which they occur. See order, you see, first I have taken 2, next 3, next 3, next 3. But here first I have taken 3, next 2, next 3, next 3. So order may be different, but prime factorization is unique. That means prime factors occur. What the prime factors occur, it is unique. Unique means same. It does not change. So here 54 is expressed as product of primes. Is it right? So how many primes are there here? 2 is a prime, 3 is a prime, 3 is a prime, 3 is a prime. So it is expressed as product of 2 or more prime numbers. So when any number is expressed as product of 2 or more numbers, more prime numbers, then it is a composite number. So here 54 is a composite number. Did you understand, children? So why I told this theorem means next sum is related to this concept. So in exercise 1.2 we have explain model sums. I am saying, remember children, I won't say anytime textbook sums, only model sums I will say. From that you do the remaining sums. 8 into 5 into 4 into 3 into 2 plus 5 into 4 into 3 into 7. Explain why it is a composite number. They are saying it is a composite number, but you have to explain why it is a composite number. Here we have two methods. What is the first? Actually I told what is a composite number? If a number is expressed as product of primes, that means 2 or more primes, then it is a composite number. So here we have two methods. See, up to plus before 1, up to plus after 1. Two parts are there. We can do in two methods. First method is, first we have to multiply all the numbers. Here you have to multiply all the numbers. Both you add. Then you do prime factorization. If the number is expressed as product of 2 or more primes, then it is a composite number. Here, but I am explaining in another method. Here, two parts are there. No? In these two parts, what is common? 5 is common, 4 is common, 3 is common. So I will write 5 into 4 into 3. If you take out 5 common, 4 common, 3 common, then what is left here? 8 and 2. So you write 8 into 2 plus, here if you take 5, 4, 3 common, 7 is left. So 5 into 4 can be written as 2 into 2. 8 into 2, 16. 16 plus 7, 23. 5 into 2 into 2 into 3 into 23. See here, these are all prime numbers. 5, 2, 2, 3, 23. So the given number is expressed as product of primes. So it is a composite number. Is it right? So what you have to write conclusion? According to fundamental theorem of arithmetic, according to fundamental theorem of, according to fundamental theorem of arithmetic, every composite number can be expressed as product of primes. Every composite number can be expressed as product of primes. Is it right? So here 5 8 into 5 into 4 into 2 plus 5 into 4 into 3 into 7. If we solve, it is expressed as product of primes. So what we have tried here, 8 into 5 into 4 into 3 into 2 plus 5 into 4 into 3 into 7 is expressed as product of primes. 8 into 5 into 4 into 3 into 2 plus 5 into 4 into 3 into 7 is expressed as product of primes. So it is a composite number. Did you understand what I told? You can do normally multiplication and we can add, after that we can do prime factorization. Okay, so this method also we can do. Next, for example, if they give 7 into 5 into 3 into 2 plus 5 into 3, like this they give. How many parts we have here? 2 parts. This is one part, this is one part. What will be the common here? 5 into 3. If you take 5 into 3 common, what is left here? 7 and 2. 7 2 is 14. Plus, see here, if you take 5 into 3 common, anything is not there. If anything is not there, we should not write 0. If anything is not there, we can write this one as 5 into 3 into 1. Then value does not change. If 5 into 3, if you have taken common, here 1 will be there. So 5 into 3 into 15. If you observe this, these are all not prime factors. Why? 5 is a prime number, 3 is a prime number, but 15 is not a prime number. So what we have to do? 5 into 3 into 5 into 3. Here the given number is expressed as product of primes. So the given number is a composite number. By which theorem we are saying this one? By fundamental theorem of arithmetic. Okay children? Next, explain why. I am asking, explain why 6 power 100 does not end with 0. Explain why 6 power 100 does not end with 0. So what I will do here, actually 6 power 1 6, 6 power 2 36, 6 power 3 216. So if you multiply 6 power any number, always you will get in the ones place 6 only. Here they are asking, explain why 6 power 100 does not end with 0. Why it does not end with 0? Here we have one rule. To end with 0, the prime factorization of base, should contain both 2 and 5 as factors. Why it should contain both 2 and 5? Because the combination of 2 and 5 gives 10. Suppose here 2 into 5, 10. Whenever you do 10 power anything, you will get 1 ones place 0. Next, suppose if you take 2 square into 5 square. How much? 100. 2 square 4, 5 square 25. 100 power anything will be 0. So whenever the base, the prime factorization of the base contains both 2 and 5. If you take only 2, only 5, you won't get 0. Whenever it gets 0 in its ones place, its power, whenever you are taking power 1, power 2, power 3, always you will get 0. So here, first you do prime factorization of the base. What is the base here? 6. We can write 6 as 2 into 3 whole power 100. Here if you see the prime factorization of the base, it contains 2 as a factor, but it does not contain 5 as a factor. What I told, to end with 0, the prime factorization of the base should contain both 2 and 5. Extra anything there also, nothing will happen. But compulsory, both 2 and 5 should be there. Here only 2 is there, 5 is not present. So what we have to write? The prime factorization of the prime factorization of 6 contains only 2 as a factor. 2 as a factor, but not 5. So not there, no? So 6 power 100 does not end with 0. Understood everyone? So here, to end with 0, the prime factorization of the base should contain both 2 and 5 as factors. But here 2 is there, but 5 is not there. In the same question, if they ask 30 power 80, does 30 power 80 ends with 0? First you do prime factorization of the base. 2 into 3 into 5 whole power 80. 2, 3, 6, 6, 5 is 30. You see prime factorization of the base contains both 2 and 5 are factors, no? Don't think about 3. If extra any number there also, nothing will happen. But you have to see whether 2 and 5 both are present or not. Extra elements, if they are not there also, no problem. So here if you see prime factorization of the base contains both 2 and 5 as factors. So 30 power 80 ends with 0. Did you understand? So like this you have to solve the sums. And in the last one they told what is the last digit of 6 power 100. What is the last digit? 6 power 1, 6, 6 power 2, 36, 6 power 3. How much? 216. So always the digit in one's place is 6. Did you understand, children? Today we learned about fundamental theorem of arithmetic. What is fundamental theorem of arithmetic? Every composite number can be expressed as product of primes. Prime factorization is unique apart from the order in which they occur. Okay. Next, what you learn? How to find exercise 1.2 for last 3 sums. Okay. Okay, children. Thank you. Bye.